When we think about a big scientific discovery, we usually picture a pristine lab, right? Some fancy machine humming away, and then bam, it spits out a perfect number. But the real story, the thing that makes or breaks the entire experiment, well, it happens way before any of that. It's really more of a detective story. And its hero? The humble sample. So let's follow the clues. I mean, just think about this for a second. It sounds completely impossible, doesn't it? We talk about finding a needle in a haystack, but this is like trying to find one specific marked drop of water in an entire ocean. So how on earth do they even begin to look? And right there, that's the secret. It's not about the million-dollar machine at the very end of the process. The entire foundation of a scientific measurement rests on perfectly capturing, preserving, and preparing that very first, tiny piece of reality. Because in science, it turns out the journey of the sample is everything. Okay, so our investigation starts right at the source. It could be a river, a giant pile of mineral ore, or even the air we're breathing. Scientists have to somehow grab a piece of it that is a perfect representation of the whole thing. This is step one, collecting the evidence. This first big haul of evidence actually has a name. It's called the gross sample. And it might be huge, like a giant bucket of water or literally a ton of rock. Everything that comes after, every single conclusion they draw, depends completely on this initial sample being a true snapshot of the bigger picture. No pressure, right? So how do you do it? How do you grab a water sample from, say, 100 feet down in a lake without it getting contaminated by all the water on top? Well, you use some really clever gear, like this Niskin bottle. It's lowered down into the water completely open. Then, when it reaches the exact depth you want, you send a little weight sliding down the line. That weight hits a trigger, and snap, the caps on both ends slam shut, trapping a perfect, pristine sample of that deep water. And what if you want a piece of the lake bed? Well, the tool you choose depends on the kind of story you're trying to uncover. On the left, you've got a grab sampler. It's basically like taking a quick snapshot. It just scoops up a chunk of whatever's on the surface. But the core on the right, that's more like a time machine. It pulls up a whole vertical column, showing you all the different layers of sediment that have been laid down over years and years, preserving a complete historical record. Now, for something solid, like a giant pile of mineral ore, you can't just pick up any random rock. You've got to shrink the sample way down, but keep it perfectly representative. And for that, there's this brilliantly simple tool called a riffle splitter. You just pour the whole gross sample into the top, and it gets perfectly divided again and again into smaller and smaller piles. By just taking one of those piles and running it through a few more times, you can get a totally manageable lab sample from a 1-ton pile and still be confident it represents the whole thing. Okay, so you've successfully captured your sample. Case closed? Not even close. You see, the moment a sample is taken out of its natural environment, it starts to change. The next supercritical step is to preserve it, to basically freeze it in time so that it doesn't change its story on the way back to the lab. And this table, wow, it really shows you just how strict and different the rules are for each piece of evidence. I mean, look at this. If you're measuring something like pH, you have to analyze it immediately. There's no holding time. For nitrate, you've got about 48 hours, so a couple of days. But for most metals, if you preserve them the right way with a little bit of nitric acid, you can let them sit on a shelf for 6 months. It just goes to show you, every single analysis has its own strict set of rules to make sure the evidence doesn't get compromised. All right, the sample has finally arrived at the lab, safe and sound. But you can't just stick a rock or a jar of murky water into a highly sensitive piece of equipment. Nope, it has to be meticulously prepared for its final close-up. For solids, there's another wonderfully low-tech but super effective method for getting the size just right. It's called coning and quartering. You literally pile the sample into a cone shape, then you flatten it out into a circle and divide it into 4 equal pizza slices. Then you get rid of 2 opposite quarters, mix the 2 that are left, and you just do it again. You repeat this whole process over and over until you have a small but still perfectly representative sample for the lab. But here's the thing. Most modern instruments need to analyze a liquid. So how do you dissolve a rock? Well, chemists have a whole toolkit for this. They can hit it with brutally strong acids or even blast it with microwaves inside a special high-pressure container. For the really tough stuff, they can literally melt it with a special salt called a flux or just stick it in a super hot furnace and burn away everything that's organic. We are finally at the last stage. The sample is prepped, it's ready to go, but now comes the ultimate challenge: isolating the one thing you're actually looking for. the signal from a whole chemical soup of other things that can get in the way, the noise. So to solve this puzzle, we need to know our two main characters. The analyte, that's our target, that's the chemical suspect we're trying to measure. And then there's the interferent. Think of the interferent as the imposter, the chemical that looks or acts just enough like our analyte to fool the detector and give us a totally false reading. Here's a perfect way to think about it. Imagine trying to measure the amount of glucose in honey. That's actually pretty easy to do. If, and this is a big if, your method is smart enough to ignore the fructose. See, fructose is an interferent. It's a different sugar, but in some tests, it can look just like glucose. So the entire goal is to make your measurement blind to the fructose, so it can only see the glucose. This right here is the dream scenario. The total signal that the machine sees is directly related to the amount of our analyte, our suspect. The more analyte you have, the bigger the signal. It's clean, it's simple, it's direct. But of course, here's reality. The total signal is actually the analyte signal plus a false signal from that pesky interferent. That second part of the equation, that's the noise. That's the problem. And all that hard work, the careful sampling, the preserving, the prep, it's all designed to get rid of that noise, or at least make it so tiny that it doesn't even matter. So let's look at a real-world case study and see if all this effort actually pays off. In this case, scientists wanted to measure copper, but there was a bunch of zinc getting in the way as an interferent. So they came up with a separation method to get rid of the zinc before the final measurement. So how'd they do? First, let's look at the analyte recovery. How much of their target, the copper, did they manage to hold on to? They kept 98.91% of it. That is a fantastic result. They barely lost any of their suspect during the entire process. And this is the real victory. What about the interferent? The zinc? They successfully got rid of almost all of it. Only 3.2% of the original amount was left to create any noise. They got their man, and they cleared the room of any imposters. So the verdict is in. By focusing on that painstaking, careful process of sampling and preparation, they made sure that the final number their fancy machine spit out was accurate, that it was trustworthy. It really proves that old saying in chemistry, the result you get is only ever as good as the sample you start with. So I'll just leave you with this. The next time you see a scientific headline with some really precise number, maybe you'll think past the gleaming, expensive machine in the lab, and instead you'll appreciate the incredible, invisible journey that a single, humble sample had to take to get there.